So let's start this technical exchange. So I'd like to thank everybody for being here, and I'd like to also thank all of our speakers today. So today's CCTF technical exchange is on options for redefinition of the SI second. We're going to have a number of contributors today. So the goal of this technical exchange is to discuss and understand better some of the options for redefinition of the SI second based on optical atomic transitions. And there are a number of options that will be discussed today. So we'll have an introduction, which is kicked off by Marina Gertsvolf from the NRC. And we'll have four technical talks today discussing least squared analysis for optimal determination of frequency ratios, defining the SI second via option 1, change in continuity, defining the SI second via option 2, challenges and opportunities, as well as a final talk on fulfillment for redefinition of the SI second criteria and challenges. So we're going to be hearing from a number of members from our international community. Just as a reminder to speakers, each talk will be about 20 minutes, including question and answer. And at the end, we're hoping to have a moderated discussion between the audience as well as panelists around some of the questions that the audience might have. So I'd like to kick this meeting off and have Marina share her slides and begin this CCTF technical exchange.
Thanks, Tara, for the introduction. So this technical exchange on the redefinition is part of our technical exchange series that are organized by all different working groups and subgroups. This one specifically is from part of subgroup 3 on education and communication efforts. So I'm going to give you a quick introduction. So the SI second was defined at the 9th resolution of the CGPM in 1960 as 1 second of the fractional part of the tropical year of 1900. So you can see this was based on astronomical observations. Then very quickly in 1967, when it was realized that the atomic frequency is much more precise than astronomical, much more stable than astronomical measurements, the SI second was redefined using the atom of cesium, using the specific transition frequency between the two hyperfine levels of the cesium atom. And then after many more years, in 2018, just the wording of the definition of the SI second was changed to align it with the same approach to the wording of other basic units in the SI system that were redefined at that time. But we still work with the same definition of SI second through the frequency of the cesium atom. And here is an illustration of the first operating cesium clock at NPL, photograph from 1955. So very close to the definition in the 67. So this is the graph that you all have seen many times. This is the evolution of atomic clock precision as a function of year. And you can see in blue squares are the microwave cesium clocks. And this is how they changed the accuracy over the decades. And the red circles, both dark and light red circles, are the optical clocks. And you can see that they started in the 1990s and had a very rapid improvement in their performance, surpassing the accuracy of the microwave clocks in the mid-2000s. And from that point on, which I indicate here approximately as with the yellow arrow, this is the point when optical clock frequencies optical clock frequencies exceeded the accuracy of the microwave clocks that were available. This is the time when the time and frequency community realized we need to redefine the second. And so it took a few years, but in 2017, the first roadmap to the redefinition of the second was proposed and adopted by the presented at the CCTF meeting and was adopted by the CCTF. You can see there are a list of different conditions that had to be met, and the target date for the redefinition was, I think, CGPM at 2026. At that time, the CCTF community went further and created task force on the redefinition, and in 2020 presented a list of criteria, both mandatory, that's the top red boxes, and the desired criteria, but not mandatory, for the redefinition of the second. And it expanded on the redefinition roadmap that I showed you earlier, with more specific, precise, targeted definitions that concern on different aspects. So this, for example, conditions to change that are related to frequency standards and TEIs, conditions related to comparisons of the frequency standard and the dissemination of the SI second. And the third one is the acceptance of the criteria of the redefinition. You can see there are quite a lot of mandatory criteria. There are a few desired criteria, but we also committed to meet the mandatory criteria in the community. So this was done in 2020. And things looked very, very promising. Very focused in the timing and frequency community among NMIs, that the CCTF submitted a resolution to the CGPM that was accepted, that was issued in 2022, CGPM 2022, resolution number 5, that encourages the International Committee for Weights and Measures, CIPM, encourages to promote the importance of achieving the objectives in the roadmap for the definition of the second. Also, it encourages to bring proposals to CGPM 2066 for the choice of the preferred species or ensemble of species, and take the further steps towards the new definition to be taken in 2030. And invites, of course, member states to work very hard to meet this criteria. So this was a very positive, optimistic view that we have in 2022 with the CGPM resolution, which we were working towards to fulfill. But I'll show you again the timelines where we are. So this is when we needed the new definition. This is how fast the redefinitions happened in the past. So I showed you before 1960 the definition that the SI system introduced. This is when the astronomical time changed to atomic time. Here we go in a little bit slower. So this is when redefinition is needed, because atomic clocks, optical clocks are better than microwave clocks. The first roadmap is created. Then the redefinition option is targeted to be selected by the CGPM resolution in 2026, with the redefinition taking place in 2030. That's the goal of the CGPM resolution number 5 in 2022. So we have a wider spread of years. This is to ensure that preparation work is done thoroughly to prepare for the redefinition, because we know it can last decades. So the task force on the redefinition comprises of 3 groups that focus on different aspects. I'll tell you about it. But the important thing is that these groups are large, and they include members from all around the world, from national metrology institutes and NMIs, and also experts from academia from all around the world. And each group, subgroup, is chaired by several people. I'm listing them here. You all know them. You can. Some of them are presenting today, and you can ask them questions afterwards. And this subgroup members work really hard to prepare for the redefinition. So subgroup 1 on options is tasked with define different options for the redefinition, provide analysis on options and species, and make proposals toward the consensus of the choice of options and species. Subgroup 2 on criteria is to monitor redefinition criteria fulfillment levels, progress, and identify criticalities and propose mitigating actions. And the subgroup 3, which organized this technical exchange for you, is to develop communication information and tools related to the definition of the for CCTF, NMIs, UTCK labs, and the general public. So what are 3 different options that you will hear about more? Option 1, single transition. Option 2 is a geometrical mean of different frequencies, and there are even option 1 to 2A and 2B, fixed or flexible or live choice of this different species in the ensemble. And option 3 is fixing a numerical value for additional one fundamental constant. And this option would have been the best, because it would align with current definition of all other SI units. But unfortunately, at present, the fundamental constants that we have values for are not known precise enough without reducing the accuracy of the SI second by 4 orders of magnitude. So that's, unfortunately, option 3 is not feasible at the moment. So I told you that subgroup 2 is looking about the fulfillment of the criteria, mandatory criteria and optional as well. Here is only mandatory criteria is listed. You know, group 1, group 2, and group 3. And you can see that this is the fulfillment level progress of this criteria. We want to be above this dashed vertical line to actually be happy with the progress of the redefinition. When the redefinition happens, we want to have this fulfillment achieved. And we don't want to sit here in the red zone or even red-orange zones. We want to move steadily forward in this redefinition. But you can see that there are still some challenges that you will hear about more today, I'm sure. So what has been done? We had many meetings of the strategic planning working group and the task force on the redefinition, talking about all different aspects of the redefinitions. Just the task force met 10 times since 2020. Multiple meetings of the subgroups, multiple CCTF meetings, technical exchanges, conference plenary talks. Many of this access to this information is available through the CCTF website. Many of the talks and presentations are recorded. And the questions remain that we have to resolve in the near future. Do we select option 1 or option 2? If option 2, option 2A or option 2B? Which species and when? And this is the timeline of the redefinition. If we want to meet, this is an example of the frequently asked questions that you can find on the CCTF webpage dedicated to the redefinition. It's quite easy to find it. It's open to the general public. But this first question, I think it shows you an example of the timeline of when different events need to happen in order for the definition to actually happen in 2030. So take a look at that. This technical exchange is organized now in April, in the end of April, to allow all the attendees from all the CCTF member institutes and the observers to prepare for the next meeting of the CCTF when this details of different options and species will be presented, and some decisions will need to be made. So listen carefully to these presentations that follow, and more importantly, ask questions and participate in the discussions, and go back to the recordings of the different sessions and talks, and to the frequently asked questions, and have all your questions answered. And with that, I will pass on the presentation to Helen, who will give the first technical talk about the least square analysis for optimal determination of frequency ratios. And thank you very much.
Thank you, Marina. I will just share my screen. Hopefully that's okay. Can you see that?
Looks good, Helen.
Yep. Okay, great. Thank you. So yes, thank you, Marina, for the introduction. And as advertised, I'm going to talk to you today about least squares analysis for optimal determination of frequency ratios. So this is important in the context of the roadmap for the redefinition of the second, and in particular, it's essential for these first 2 mandatory criteria that we need to meet before redefinition. So that's the validation that optical frequency standards are at a level 100 times better than cesium primary standards, and ensuring the continuity of the new definition with the current definition based on cesium. So meeting these criteria requires frequency comparisons to be carried out between optical clocks developed independently in different laboratories around the world. And these pictures just illustrate some of the largest scale comparisons that have been performed to date. Bilateral comparisons are important too, and they are being carried out by a number of labs. So the global body of clock comparison data is used by the CCTF Frequency Standards Working Group to derive the values that are given in the list of recommended values for standard frequencies, which is published on the BIPM website and updated periodically as new and improved data becomes available. And this list includes recommended frequency values and uncertainties for secondary representations of the second, which are used when the optical clocks contribute data to the BIPM for steering of international atomic time. So they're already very important even before redefinition. The challenge is that deriving these values, the clock comparisons result in an overdetermined data set. And what I mean by that is that it's possible to deduce some of the frequency ratios from the results of several different experiments. So, for example, if I have a collection of standards based on 4 different reference transitions, as shown here, I could measure 𝐤1 over 𝐤2 directly, or I could deduce it from combining 2 other measurements against a common clock, such as 𝐤3. And so for 4 different standards, 6 different frequency ratios can be measured. If we increase the number of standards to 6, there are 15 possible measurements, and for 8 standards, there are 28. But in each case, the number of independent frequency ratios is just 1 less than the number of standards involved. So, of course, in practice, not all frequency ratios are measured, but overdetermined datasets did become a reality about 10 years ago. So, in 2015, the Frequency Standards Working Group was facing a situation where, really, for the first time, the data set they needed to analyse was overdetermined. So there were measured optical frequency ratios available to them in addition to absolute frequency measurements relative to cesium primary standards. And the indirect determinations of some of the frequency ratios had comparable uncertainties to the direct determination. And that meant that some of them, all of them really needed somehow to be considered in deriving a best value for the frequency ratio. So by 2017, 8 frequency ratios not involving cesium had been measured, and some of them had been measured more than once. And by 2021, 14 different ratios had been measured. So that meant really new methods were required for analysing these overdetermined sets of clock comparison data in order to check the level of internal self-consistency and to derive optimal values for the ratios between their operating frequencies. So the method we use is a least squares analysis procedure, and it's based on the approach that CODATA used to provide a self-consistent set of recommended values of the fundamental physical constants. So the input data to this least squares adjustment consists of a set of frequency ratios. So those could be optical frequency ratios, microwave frequency ratios, or optical to microwave frequency ratios. And whatever kind they are, they're all handled in a similar way. We just treat absolute frequency measurements as a frequency ratio that involves a cesium primary frequency standard. So ratios with cesium are not treated as special in any way in this analysis. The conversion to hertz to give the recommended frequency values just comes as the very last step of the calculation. And a final point, the algorithm is also capable of handling correlations between the measurements where they're known. So, in a bit more detail, the input data to the least squares adjustment is a set of n frequency ratio measurements between clocks based on ns different reference transitions, together with their standard uncertainties and the correlation coefficients between them, from which we can compute their variances and covariances. So as a first step, what we do is to express the measured frequency ratios as a function of one or more of a set of ns-1 independent adjusted frequency ratios, which leads us to a set of n equations. And it's the values of the adjusted frequency ratios that are optimized in the least squares adjustment. So in most cases, the equations relating the measured frequency ratios to the adjusted frequency ratios are nonlinear. And that means that to apply linear matrix methods, we have to linearize the equations before the least squares adjustment by using a Taylor expansion around initial estimates of the adjusted frequency ratios. That linear approximation means that the best estimates for the values of the adjusted ratios that we get out of the calculation are not actually exact solutions to the original nonlinear equations. But we can use these values as starting points for a new linear approximation and then iterate the least squares adjustment procedure. And we go around that loop until the values of the adjusted frequency ratios converge. So at that point, we can calculate any other frequency ratio of interest and its uncertainty from the adjusted frequency ratios and their covariance matrix. And we can also perform consistency checks by looking at the normalized residuals and the Burge ratio. So I'm not going to describe the math of the adjustment in detail. You can find it all in the paper that I've referenced here. So these methods were used for the first time in 2015 to update the list of recommended frequency values. But what wasn't ideal at that point is that there was only one algorithm and software available, so no independent cross-checks of the results were possible at that point. So by the time of the next update in 2017, the situation was a lot more satisfactory. We were able to perform 3 independent calculations using 2 different algorithms, and fortunately, they agreed. However, at that time, correlations were almost entirely neglected in the calculations and the update to the list. And as we'll see in a moment, that's not good. So in the next update, performed in 2021, that's the most recent update, we faced up to that issue and we gave correlations proper consideration in the calculations and we took it into account in the analysis. Some other changes, reflecting the increasing importance of the optical frequency ratios for verifying the international consistency of optical clocks. We also, for the first time, provided all the ratios as an appendix to the list of recommended frequency values. And finally, in assessing the input data and considering the uncertainty that we needed to assign to each recommended frequency value, we slightly modified the rules and the criteria that had been used in the past to ensure that the output data set, which consists of correlated absolute frequency measurements and frequency ratio measurements, was internally self-consistent. And so it's this 2021 update that I'm going to focus on now. So the analysis underpinning this update was performed by a small subgroup of the Frequency Standards Working Group that you see pictured here. And the full details of what we did are described in this Metrologia paper. First of all, I already mentioned we're now able to do 3 independent calculations using 2 independent algorithms. The first algorithm is the least squares one I already described, and we've got 2 independent implementations of this algorithm, one of them written in MATLAB and the other in Mathematica. The second algorithm is based on looking at closed loops in a graph theory framework, and we used a single implementation of this one for the computation. And maybe one point is that due to the extremely high accuracy with which frequency ratios have been measured, we have to take a lot of care to perform the numerical calculations to sufficiently high precision, so more than 18 significant figures. And we achieved that using routines that were specially designed for high precision floating point arithmetic, because standard double precision floating point arithmetic is not enough. And the results that we obtained using the 2 different implementations of the least squares algorithm differed at most by 1 significant digit, by 1 in the least significant digit of the computation, that's the 24th digit. Slightly larger differences were seen in a few cases between the results obtained using the 2 different algorithms, but even in that case, the agreement is several orders of magnitude below the uncertainty in the output values. So good enough, at least for now. So the reason that we needed to include correlations in the analysis is that ignoring them can lead us to biased frequency values and underestimated uncertainties. So these correlations can come from either statistical or systematic uncertainties, or both. So to give you a few examples, there might be correlations between the frequencies of clocks based on the same atomic species if common theoretical or experimental values of atomic coefficients are used to correct for systematic frequency shifts, or remote comparisons using different clocks in the same institution would be correlated due to a common relativistic redshift correction. And then a final example, and actually one of the most significant sources of correlations, is common data. So for example, if several ratio measurements involving the same clock are performed at the same time, or if different absolute frequency measurements use TAI as a reference, even if they're performed several months apart, that's because the same fountains contribute to TAI month after month, and full re-evaluations of their uncertainty budgets are quite infrequent. So the input data for the 2021 least squares adjustment included the results of 105 frequency comparisons. 33 of these were frequency ratio measurements not involving cesium, and 72 were absolute frequency measurements. And we computed 483 correlation coefficients between these 105 measurements. And those correlation coefficients also formed part of the input data. Most of those correlations were between measurements that involved primary or secondary frequency standards that were also used to calibrate the scale interval of TAI. And the rest arose from other sources such as common data or common coefficients, and those ones were computed on an ad hoc basis. And importantly, including the correlations did make a significant difference to the output of the least squares adjustment. It shifted the recommended frequency values by up to 0.8 sigma and underestimated their uncertainties by a factor of up to 1.6 if we neglect the correlations. So we also made modifications to the uncertainties of a few measurements in the input data set, and that was for several reasons. One, to avoid otherwise unphysical values of correlation coefficients, to make data points identified as outliers statistically more significant with the consistent with the overall body of data, and to take account of the sparsity of the input data for some atomic transitions included in the adjustment. So the final recommended frequency values adopted by the CCTF in 2021 were the ones where correlations between the input data were included, and most of the recommended frequency values are also strongly correlated, as you can see from this heat map. Now, following this latest update, 6 optical secondary representations of the second now have uncertainties of 2 parts in 10 to the 16, or just below. That's essentially the same as the best cesium primary frequency standards. What that means is that optical clocks are now able to contribute to TAI with a similar weight to that of cesium primary frequency standards if they can achieve similar uptimes. But although recommended frequency values are what matter when secondary frequency standards contribute to TAI, optical frequency ratios are critical for verifying the international consistency of optical clocks as progress is made towards redefinition of the second. And so what we did was we also published a complete set of frequency ratios consistent with the 2021 recommended frequency values, taking into account the correlations between them. And from the point of view of this discussion, the ratios are also important when discussing options for redefinition of the second. So as you've already heard, there are 2 options still on the table, which you'll hear more about today. So option 1 is to choose a single optical transition to replace the cesium hyperfine transition, fixing the numerical value of the frequency of that optical transition to be n hertz, where n is the defining value. Option 2 is to create a defining constant based on several transitions rather than a single one. And in this case, the proposal is to use a weighted geometric mean, with the weights and the constant n being the defining values in this case. And option 2 has these 2 variants. In the first, the weights in n are fixed once and for all, whereas in the second, they're periodically updated by the CIPM following predefined rules adopted by the CGPM. But whatever option selected, the least squares adjustment procedure I've just described to you will play a key role, because one or more of the frequency ratios from that least squares adjustment will be used to set the defining constant or constants appearing in the new definition. And the frequency ratios from the least squares adjustment will be used in the mise en pratique for the new definition. So really, the key message I want to leave you with, as we move on to the rest of today's presentations, is that more scrutiny is needed on the evolution of these frequency ratios values between adjustments if we're going to ensure the stability of the new definition and realisation of the second. So thank you for listening. I'll hand back to Marina or on to next.
Thank you, Helen, for the wonderful talk. I'm curious if you would mind minimizing your, or maybe,
sorry, yeah, I'll stop sharing.
You.
Yep.
Are there any questions for Helen regarding her talk?
If I may ask a question, thank you, Helen, for this nice presentation. Do you have planned to make an update, in 25?
Yes.
Of these ratios, and also continuing between 25 and 2030 to see the evolution and the consistency of the results.
Yep. So there is a plans have just underway for the next update, which will happen at the CCTF in 2025. So September this year, we would expect to be putting a resolution to the CCTF for an update to the values. So at the moment, we have gathered the input data, and now we're just starting to work out how we handle it all and start to think about the computation of the correlations.
Yeah, it's a wonderful job. So, yeah. And my second question would be with respect to the criteria. Maybe this will be discussed later. I don't know. With respect to the criteria listed by Marina from your table, can you say something about how many of these criteria are fulfilled, or how far are we, in some example or some others?
Okay, so maybe you saw a little bit of there, and I expect Stefan is going to cover this in a lot more detail. But for example, some of the ones that are furthest from being met at the moment are the regular contributions of optical frequency standards to TAI, where actually the numbers have dropped off a bit in recent years. We kind of went through a peak in about, I think, 2022. And also the validation of the optical clocks through the international comparisons, where actually not all data is yet published, but we start to see that maybe clocks are not agreeing quite as well as their estimated systematic uncertainty budgets agree. But of course, ATIS is now also going to be able to be used for this mix, I hope, and we'll start to see the possibilities to compare clocks better on different continents. So I hope, hopefully it turned on okay today.
We'll see.
Are there any other questions for Helen?
Yeah, I have a question. So if I took it correctly there, you're saying that this analysis led to consistency with all of these different ratios. But certainly there are experiments where there is certainly questions to be asked, right? So in the Bacon collaboration, for example, there's an underspread of one ratio, an overspread in another ratio, and a correlation with the strontium density shift. Now, they are strong, compelling reasons to question the legitimacy of that data. And so is any question of that, does anybody just measure a ratio and that gets folded into this analysis?
It gets considered. It doesn't automatically get so we don't guarantee consistency, because to bring some of the results into consistency, we end up having to expand some of the uncertainties in a similar way that co-data do, in fact, where they see inconsistencies in the bodies of data. But this is partly the role that the Frequency Standards Working Group play, is to scrutinise that data. And it's also the reason why we insist And of course, this is not perfect, but we insist on data being published or accepted for publication before it's included in the analysis.
Publication can't be an only metric here, right? If you read the reviews of that paper, one of the reviewers acknowledged the inability to reproduce the data, but said that's okay because everybody's having that trouble, right? That was what the reviewer said. So something getting into a publication is not a very good metric for whether or not the scientific integrity is being upheld.
It's like I said, it's not perfect, but it's better than not having it published at all. I think we probably shouldn't get into the details of specific publications here, but I know they did expand uncertainties in that publication to try and take account of the data. And if we start seeing inconsistencies with new measurements, we will have to work out how to deal with that as part of the analysis.
But the question becomes, what is an inconsistency if you're just expanding the errors to incorporate these? Like, what do you call too much of an inconsistency before you say, there's a problem here? Most people would say it's the reduced chi-squared, and then you've got a problem, and then you address it. But if you're just going to expand the errors to get around that problem, there's no end to that.
Well, like I said, it's similar to what CoData do, because we're just trying to produce the best values we can from the information available. And you're right, one of the big challenges here is the scarcity of input data. And I think that's one of the issues we need to discuss when we think about, if we went for option 2, which systems would we put into the ensemble?
Okay.
Yep.
Okay, thank you. I think it's time to move on to the next speaker. So we'll have the next speaker will be Ekkehard Peik, and he will be speaking about defining the SI second via option 1, change and continuity. So Ekkehard, if you can start sharing your screen.
Can you see it now? Slides?
Perfect.
Okay,
thank you.
Great. Yeah, good afternoon. It's my pleasure to speak a bit about option 1. And you may say, okay, this is well-established methods that we are using already, but I'd like to explain a little bit of how it can be implemented and what we can expect from the implementation. So let's have a brief look at the previous definitions. Of course, it was mentioned already. We had the astronomical definition, and then the switch in 1967 to the atomic second defined via cesium. I'd just like to add a little side remark. So the definition itself was rather compact, and a number of important things were not implicitly included, but of course understood. That first of all, this is proper time defined here, so it does not make reference to a specific relativistic system, and also the atom is assumed to be observed under idealized conditions. For example, in the absence of external electromagnetic field, something that turned out to be later quite critical in order to be understood and to be implemented. In 2019, all of the SI system underwent a redefinition for the second. It just meant that the wording of the definition was changed in order to have a uniform wording with the other units, but the content was not changed. So the new wording, you can see it here, the same number of the frequency and the cesium 133 atom, but now in a slightly defined wording. This was with the purpose I mentioned to obtain a uniform structure, and the structure is shown here. So all the base units are now defined via the value of a fundamental constant. And so the numerical value of this constant is fixed, and this then the product of the number and the unit defines a constant, and so this is used for the definition of the unit, and the realization is left open for certain technical choices that can be made independent of the definition. So looking at this structure, it kind of elevated, I would say, the importance of the cesium hyperfine ground state splitting, this 9,192 million oscillations per second, because now we can see it as the same footing as the speed of light or Planck's constants or the elementary charge, where from a fundamental physics point of view, one would say these are really the key fundamental constants. So the cesium constant now, of course, it is obviously quite important. It plays a prominent role in the system of the SI system. And of course, it was said at the time already, preserving continuity is an important criterion for the system. It should be done as much as possible. I'd like to briefly look back at how this cesium frequency was determined actually, and this was done in the second half of the 1950s. From a precision measurement involving the very first operative cesium clock at NPL. And this was compared with measurements of the astronomical timescale performed at the USNO in Washington with the device shown here, the so-called dual rate moon camera that measured occultations of stars by the moon. So an individual measurement over one day gave an uncertainty of maybe 100 milliseconds with this device, so 10 to the minus 6 uncertainty, but the measurements were continued over several years. And the end result was then published here in volume 1 of Fusrev Letters, stating an uncertainty of about 10 to the minus 8 for the cesium transition frequency expressed in terms of the ephemeris second. So an uncertainty of about 20 cycles. And then the result of this measurement was then used in the 1967 redefinition by setting the uncertainty to 0 and using the result of this measurement for defining the duration of the SI second in terms of cesium oscillations. And this important measurement was in fact a unique effort. I think it has not been repeated, and I think this made sense. So because the dominant causes for the uncertainty, as they were at the time, they persisted. It was the irregularities in Earth rotation rates, the difficulties of the astronomical observations, and of course also the difficulties of linking to the historic definition of the ephemerides. Now let's go to the discussion on the redefinition, and I've listed here a little bit of the tasks that the goals that should be achieved. So now we want to exploit the advantages of the optical clocks, their higher accuracy and stability. This shall enable improvements in the realization in the unit of time and of time scales. Of course, we want to maintain the continuity with historic frequency measurements and of course with time scales. And the new definition should fit into the structure of the 2019 SI system. So this sets like the framework of requirements that we have in discussing the options for the redefinition. And so the option 1 that I'm discussing here is mainly based on selecting a new reference transition. It will be now an optical reference transition in a suitably selected atom or ion, and it will replace the status of the ground state hyperfine transition in the cesium atom. And of course, related to this is a new determination of the numerical value in Hertz that is used in the definition. It will no longer be the 9,192,000,000, but it will be a newly determined value corresponding to this optical frequency. And of course, it will be determined in maintaining the continuity of the duration of the second as well as possible. So what would be the steps for implementing this option? The first step will, of course, be the selection of the new reference transition. And the framework to select this transition could likely be the candidates that are evaluated and monitored already as the current secondary representations of the seconds. There is about a field of about 10 transitions that are considered. This still leaves a relatively wide choice of transitions, and so the choice should be based on, I suggest initially, some as much as possible objectifiable criteria that are already generally considered for the redefinition and for the option and for the redefinition. So I'm just listing a few of the possible quantitative criteria here. So of course one would try to select the lowest possible systematic uncertainty. The uncertainty budgets should be consistent over measurements performed with different devices in different laboratories, verified in comparative measurements. One would look a little bit at the history already of the frequency standards. So one criterion could be the accumulated weights of TAI contributions that have been performed with a specific transition. This would include the number of laboratories involved, number of laboratories actually contributing, reporting their standards to the BIPM, the systematic and statistical uncertainties that are achieved in these reports, the reliability in operation, that is how much of a duty cycle can be obtained with such a standard over the operation interval of 30 days, and all these things would be accumulated and investigated. And of course, this list is not conclusive. There will be other additional criteria. In case that one ends up having several candidates where these figures turn out to be rather similar, then it will not give a unique criterion for the selection. And at this point, I think it will be really a question of discussing and then possibly voting in the committees. The second step then for the implementation would of course be the determination of the numerical value for the defining constant. And this was already mentioned in Helen's presentation. So it will be based on the CCTF evaluation of the absolute frequencies and ratio measurements. The new standard, of course, should be related to the cesium frequency. So the expected uncertainty in the defining constant will likely be related to the lowest uncertainty from the absolute frequency measurements. So in the low 10 to the minus 16 range, corresponding to maybe 100 millihertz. And again, for the definition, one would set this uncertainty to 0. And again, that's why I make this historic comparison. This procedure would be unique. It would not be required to repeat it later, because the causes for the uncertainty in this number, which is the uncertainties in the best available primary cesium standards, is very likely to persist and not to change significantly. Now, for a few questions: what will be the consequences of the procedure? For example, what about the other candidates? So there will be a primary candidate will be selected. What will happen to the other candidates that are not selected for the definition? Well, of course, these can continue to be used and operated as secondary representations for the second, for all kinds of applications. For example, also for TAI calibrations. And I'd like to point out the consequence here. So why the uncertainties right now is in the range of the low 10 to the minus 16, with which these standards could optimally contribute to an TAI calibration. The table here lists the present recommended relative uncertainties of the secondary representations. After the redefinition, the uncertainty will be determined with respect to the primary, and then possibly it will be in the low 10 to the minus 18 range. If we expect that the uncertainties do not vary very much between the primary and the secondary, then a secondary will just have roughly a factor square root 2 higher recommended uncertainty than the primary standard. So they can contribute to TAI calibrations very much on a competitive or similar footing as a primary standard. The recommended frequencies or frequency ratios are, of course, then obtained from the adjustment of the measured optical frequency ratios, as just explained in the presentation of Helen. So it means that the metrological value of all of these secondary standards therefore increases significantly with the redefinition. It's not that they are losing of their importance or of their usability. Their metrological value will rather increase. What will happen to cesium clocks and the cesium infrastructure? Of course, cesium will lose the status as of the primary standard, but very naturally it can become a secondary standard with a frequency, as we know the number as it is today, and it can continue to be used in all kinds of measurement systems, including for the realization of the second. So there is no losses in the usability or importance of the existing cesium clocks or microwave infrastructure. The uncertainty of the secondary, of course, will be then be determined by the uncertainty of the cesium, by the systematic uncertainties of the cesium clocks. So for the best primary cesium clocks as we know today, the uncertainty will again be in the low 10 to the minus 16 range. Then another question that is discussed in contents of these options, isn't it that a lot of work and knowledge that has been obtained now in research on the other systems will be uselessly lost by selecting our single transition as a primary standard? And I'd like to discuss this question a little bit with an historic look at what happened before and after the 1967 discussion for the redefinition. You can see the picture here of the CCTF committee meeting in 63 in Paris. You can recognize on the left Norman Ramsey and Louis Essen. So at the time, this is from a paper that 𝐤𝐤𝐞𝐫 is just preparing. This shows the types and numbers of standards that were operative at the time. So cesium was dominating because of the commercial cesium clocks that were available already. But in addition to cesium, there was ammonia masers, hydrogen masers, thallium beam, rubidium beams. And if you look now at the fate of these other standards, we notice that the work on ammonia and thallium was indeed gradually discontinued after the redefinition, as it showed little progress and fell behind the performance of the cesium. But on the other side, hydrogen masers and rubidium clocks did just great, and their development and their use continued until today, as they were superior in specific specifications over cesium, like for hydrogen masers, the short-term stability, for rubidium, the size and the price and size of the clocks. So I think the example shows that work developed in other systems is not lost and may continue to be useful and to be fruitful for science and applications. Now, looking a bit further, how would the system of the primary and secondary evolve after the redefinition in a number of hypothetical events that could happen? For example, a previously unknown problem could be recognized in the primary standard. And this is something that happened with cesium in the 1990s, when the problem of the blackbody radiation was understood, and when it was realized that the effect would actually now be relevant on the scale of the accuracy of the best cesium clocks at the time. Or what would happen if all laboratories, by some coincidence, stopped to operate the standards related to the primary? Now, the first problem, the definition clearly refers to the unperturbed atom. So there's a clear indication of how such a problem should be addressed. And then one should see how big is the problem, can it be addressed or maybe not. In the second case, maybe that could be a practical problem. If nobody operates a primary, of course, it would not be attractive to use it for the redefinition. So this is scenarios in the worst case that could lead to a switch of to the requirement to have a switch of the primary standard. But other possible events, like for example, a problem appearing with one of the secondary standards, so a previously unknown problem, or laboratories just ceasing the operation. This would just mean that that the committees have to, if there is an unknown shift, the recommended frequencies would have to be adapted, or a candidate that would not perform or would not be operated anymore could also be withdrawn from the list of secondary representations. It would have no effect. There would be no requirement to change the definition. In the positive side, if a new previously unknown system that very promising or superior properties is found, again, the system is flexible, so the committees may recommend the standard, the frequency may be measured in relation to the primary. The new candidate may be placed on the list of the secondary and can then fully contribute as a secondary standard to timescales and frequency measurements, again, with no effect on the definition. So this is a few of the scenarios that show how this option could evolve in the more mid and long-term future. So with this, I'd like to summarize. So I think the option 1 promises to fulfill the main achievement goals that I have listed. So it will benefit from the high accuracy and stability of using an optical frequency standard. It will make use of the ability of the variety of primary and secondary standards. It ensures a seamless integration of the existing microwave infrastructure. Cesium can be continued to be used as it is today. And also, I think quite important, it presents a definition that is familiar to the whole community of metrologists, even from the other fields. And I think this is because the definition, it follows a scheme that is common and well understood in the whole world of metrology. So I think it combines several of these advantages in the continuity, and the system will also be adaptive for future developments in the field. Thank you very much for your attention.
Thank you, Ekkehard, for the wonderful and full talk. Thank you for also presenting information about the pros and cons of option 1. I'd like to open up this talk to questions from the community. Does anybody have any questions for Ekkehard?
Question?
Yes.
Yeah, thank you very much, Ekkehard. That was a very nice introduction. Don't we, if we go prioritize a single standard, don't we give up a strong motivation to have continuous confirmations of clocks through the non-trivial frequency ratios? Because at the moment, we would isolate the clocks on the various continents if we basically assume that everything will be strontium to strontium comparisons. And we've heard from Murray before, there is still some residual inconsistency in the frequency measure.
Well, as I mentioned, so the options for the evolution of the system of secondary. So I would expect that, of course, the comparisons of secondaries will continue, and people very likely will continue to measure frequency ratios and check their consistency, and I think this data will be monitored, and in case a problem or an inconsistency appears there, the community will certainly discuss and will see if any actions are required. So from this point of view, I don't see a specific danger that something could be overlooked. Of course, in general, one may ask, would there be a reduced motivation of doing ratio measurements? But I expect that a number of secondary representations will be operated, and in this way, data will be generated that could be used in a continuous monitoring of the ratios.
Okay, thank you very much. Let's hope for the best.
Are there any more questions for Ekkehard? If not, oh, I see a hand.
one. I will ask one. And thank you, Ekkehard. That was a really great talk. I wonder, so to contrast with, say, option 2B, for example, which would update more dynamically, and if better optical clock emerges in the future, that would naturally be incorporated eventually with the appropriate oversight into the definition of the second. In contrast with that, if we pick a standard today, how does that sit with things like the thorium clock, which is on the horizon and has the potential to be extremely accurate in the future, but isn't ready to be the definition yet? Do we then do this process again in a few years' time, or is that a feature of this rather than a problem?
Oh, thank you for asking about the thorium clock. Yes, I would expect that the process would remain open in the sense that if there's really a clear indication of a clock that is better in performance, or maybe that's easier to operate, that could be also a very important criterion. Then I think one will have a discussion about a redefinition. But so in this sense, I would say the scenario is open for such a discussion, but I would not expect it to happen frequently or on a short time scale. If you see now we have discussions for 10, 20 years going on, again, I would say people would really consider seriously over a time span of 10, 20 years, is a new candidate really better? Does it lead to an improvement? Finally, the SI system is of course mainly intended for the practical use. So I think in that case, it would be really the question, is there a practical use case for switching the standard? And if there is a clear advantage for that, then I think it will be done. But I guess people will be conservative and they will not do it frequently and quickly.
All right, thank you.
Any last questions for Ekkehard? If not, if you have any more questions, please feel free to put them in the chat. We are going to have a moderated discussion at the end. So if anything comes up while you're listening to the talks, you can put them in the chat and I'll pass those chats on to Sébastien Bize at the end. So thank you once again, Ekkehard, for the wonderful talk. I'm going to invite Jerome, Lodewyck, and Tetsuya 𝐤𝐤𝐞𝐫𝐬 to launch their presentations. They'll be giving a talk on defining the SI second via option 2, challenges and opportunities. Okay.
Thank you, Tara. So together with Tetsuya, I will give you more details about option 2. So let me start with an introduction. So as was described before, the point of option 2 is to, rather than picking up just one transition, is to define the second with multiple transitions. So practically, we would be attributing weights, WY, to a number of transitions. And then the SI second would be defined by setting the geometric mean, the weighted geometric means of the frequencies of all these transitions to a given value in Hertz, whose numerical value would be n. So in this definition, WY are the weights, n is the normalization constant that is there to ensure continuity with the previous definition, just like for option 1. And this set of constants, these defining values, n and WY, they completely determine the definition. So there is no uncertainty in this definition. The definition is really given by the value of n and WI. So from a more fundamental perspective, so we have heard from Helen that when you have n different transitions and there are n-1 independent ratio, so if you combine this n-1 independent ratio together with this relation, which is the definition, then you're able to set the frequencies of all the n transitions. So this is the definition of the second for option 2. And now comes the question of the realization. So how do you realize option 2? A first idea would be to implement all the n clocks implementing all the n transitions of the definition, but it's not very practical. So a realization would rather involve building one frequency standard, implementing one of these transitions. And then the realization would be built on recommended frequencies. So here in this talk, I will write NI, these recommended frequencies, which are the numerical value of a given transition I in the SI second. And the point is that these recommended frequencies can be computed from the constants defining the unit, N and W, together with the frequency ratios that come from the global filter frequency ratio that was the topic of Helen's talk just before. So something remarkable is that these recommended frequencies, actually, they don't depend on the choice of weights and not even on the option. Whatever option you choose, whatever weights you choose, the recommended frequencies will always be the same initially at the moment of the redefinition. However, after some time, after new frequency ratio measurements and new global fit of frequency ratio that will happen every few years, then the recommended frequencies Ni will change over time. But a key feature is that by construction, the way they are defined, these recommended frequencies always average down to exactly N, the defining value of the unit, whatever the frequency ratios. And a specificity of option 2 is that these recommended frequencies come with an uncertainty that has a recommended value out of the global fit of frequency ratios for all transitions. So there is no primary frequency standard with zero uncertainty on the recommended frequency. So this is very similar to what we're doing now with secondary representation of the seconds. So in a formula, this says that the frequency of a given transition in Hertz is equal to the recommended frequency plus some uncertainty delta Ni. So all this is a mathematical definition of the option 2. So to make it a bit more understandable, so we propose a graphical representation of these relations to understand the distinction between the definition and the frequency ratio. So I give the floor to Tetsuya to describe this graphical representation.
Okay, thank you, Jerome. So let me explain about the graphical representation. Now, let me explain the graphical representation of the definition of the second. In the previous slide, we mentioned that n frequency values are determined by n-1 independent ratios and 1 relation. When there are two transitions, as shown in this figure, we can take the two axes to represent the frequencies of the two transitions. Determining the frequencies then correspond to identifying a single point in this frequency space. The least squared fitting gives the most likely values of the two frequency ratios, low to 1, along with their uncertainties. This implies that the actual frequency point lies somewhere along a line, the slope, and within the surrounding triangular uncertainty area. Here, the definition imposes an additional constraint on the point. Specifically, it provides an exact curve. In option 1, as shown on the left, the definition is represented as a vertical line, the purple line here. Since the frequency point cannot deviate from this definition line, U1 is fixed, and only U2 carries the uncertainty corresponding to the gray area. In contrast, under option 2, the definition line is a curve corresponding to the set of points where a weighted geometric mean takes a constant value. Thus, in option 2, the frequency point can move along both U1 and U2 directions within the gray area. And both U1 and U2 have uncertainties with their relative contributions reflecting the assigned weights. In this figure, the solid curve represents a case where the weight for transition 1 is 0.4, and the dashed curve represents the case where it is 0.9. As the weight for transition 1 increases, the definition curve approaches a vertical line. And when the weight reaches 1, it becomes identical to option 1. Looking at it in this way, I hope you can see that option 1 and option 2 are not doing something fundamentally different. Next page, please. Once the CIPM recommended values and the definition itself are set, they are still expected to change over time. Fluctuations in the CIPM recommended frequency values can occur when new frequency ratios are measured and a new least square fit is performed. The two figures above illustrate such situations. Under both option 1 and option 2, the gray uncertainty area changes, and accordingly, the intersection point with the definition line moves along the definition line. In option 1, this improvement corresponds to the revision of the CIPM recommended frequencies that has been performed in CCL working group frequency standards. Currently, when CIPM recommended values are revised, the cesium frequency values remain unchanged, while only the SRS frequencies are adjusted. It is important to note that under current practice, the definition line itself is never redrawn. And in option 2, this is a in case of option 2, this is a case of the option 2A. Yes. However, redefinition implies redrawing the definition line. This is the option 2B. And as shown in the graph at the bottom, in option 1, the transition being defined changes, and the definition line shifts from a vertical to horizontal line. In option 2, the definition curve must be redrawn based on new weights. A crucial point here is that even during the redefinition, the intersection between the slope line and the definition line must never be moved. Only the shape of the definition line itself should be redrawn. This ensures continuity of values. In option 2, after human selection of new weights, the curve is redrawn to preserve this continuity, and the definition value n is determined accordingly. Now, let me hand the floor over to Jerome. Thanks.
Thank you, Tetsuya. So next, I would like to discuss an important point of option 2 is how to choose the weights for each transitions. So for this, we have to look at the uncertainty and recommended frequencies. So if we go for option 1, then a specific transition, I0, that is the primary frequency standard, will have a 0 uncertainty on its recommended frequency, whereas for secondary potential of the second, the total uncertainty and recommended frequency will be the quadratic sum of the clock uncertainty and the uncertainty of the primary frequency standard. So you see here in option 1, there is a strong imbalance between primary frequency standard and secondary potential of the second, 0 uncertainty for one and combined uncertainty for the other. So the point of option 2 is to provide a more balanced uncertainty over all transitions. And the choice of weights is driven by minimizing the overall uncertainty of recommended frequencies over all transition. So the criteria is to ask that the relative uncertainty on recommended frequencies should be small or significantly small compared to the uncertainty of corresponding clocks for all possible transitions. And by performing a least square adjustment on this with this criterion, it's possible to show that the weight for the transition I should be proportional to the inverse of the squared uncertainty of these clocks implementing these transitions. So it means that most precise clocks must have a large weight in the definition. Another difficulty is that this clock uncertainty is not specific to a transition, it's specific to a device, a practical device. And so we have to determine this clock uncertainty. And the idea is to use the outcome of the global fit, which gives uncertainty on frequency ratio, and say that ideally the combined uncertainty of transition J and K should be equal to the uncertainty on the frequency ratio 𝐊𝐸 And here again, by making a square analysis, it's possible to determine uncertainties for each transitions, and then from there determine the weights. And this procedure has two interesting features. The first one is that here the uncertainty, hence the weights, is really representative of the uncertainty of measured frequency ratio. So it's really clocks that do operational measurement that set the weights of the transition in the unit, which is probably what we want for a unit. I mean, we want a unit to be practical. And also, you see, this is a procedure that looks like a three-cordon hat. So it means that in order to have a large weight, the transition needs at least two connections with two other different transitions. So it helps introducing redundancy in the determination of weights. So let me give an example. I took the outcome of the 2021 fit of frequency ratio that was presented by Helen in the first talk today. And here I write for each species, including in this fit, the recommended frequency, so exactly what Helen showed before. And for the current definition of the SI second based on cesium, here is the uncertainty on recommended frequencies. So, for instance, here for cesium, the uncertainty is 0 because it is a definition. Now, here I put the typical clock uncertainty for each transition. So, for instance, cesium, it's on the order of 10^16. And now, when realizing the second, then the total uncertainty is the combined uncertainty between the clock uncertainty in blue and the recommended frequency in orange. So it's this recommended frequency uncertainty is 0 on cesium, but it's limited by the cesium for all other transitions. So now let's assume we go for option 1, and let's pick up, for instance, aluminum ions as a new definition for option 1. So here you see the recommended uncertainty on aluminum goes to 0, so there is no orange bar, but there is some added uncertainty on the other transitions, notably for ytterbium and strontium. The same if we go for ytterbium, the added uncertainty disappears on ytterbium, but is significant on other species, and so on with strontium. But now if we go for option 2, so here you see there is no more any transition with 0 uncertainty on the recommended frequency, but all of these uncertainties are somehow reduced with respect to option 1. So we have a clear balance between all the transitions. So or on average, all are able to realize better the SI second. A notable feature is that here you see the recommended frequency. Whatever option is chosen, as advertised, they are not they do not change. So this graph was for the 2021 fit of frequency ratio with only 3 species, and already with 3 species, you see the orange bar starts to be a bit negligible, and we hope that with the 2025 fit, we'll have significant contributions from ytterbium ion and other species, which will help reducing even more this added uncertainty in the range. So I give the floor to Tetsuya for the next slide.
All right. So this Venn diagram shows the categorization of frequency standards. The left side represents the current situation of option 1, and the right side represents option 2. The reason is because regarding option 2, some people may worry that the primary frequency standards might disappear and that everything would become secondary frequency standards. That's why we are drawing this Venn diagram. And under option 2, there would be multiple defined transitions, each with non-zero weight. So in a sense, rather than losing primary frequency standards, we would gain many defining transitions. We could call these defining transition, DT here. And Claudio at Indim proposed a similar idea of wording, referring to them as co-primary frequency standards. Meanwhile, existing secondary standards would survive as transitions with zero weight, and it might be appropriate to rename them as recommended transitions for the realization of the second. Also, so far, the terms PFS and SFS have sometimes ambiguously referred either to the transitions or to the hardware devices. I think this would be a good opportunity to clarify. Frequency standards would refer to the hardware, and the transitions would refer to the atomic transitions themselves. Now, let me hand the floor over to Jerome again. Thank you.
So we'll finish by a short analysis of advantages and disadvantages of option 2 as compared to option 1. So the first clear advantage of option 2 is that we have an easier consensus. I mean, we have no arbitrary choice to make for specific transitions. Instead, every transition contributes with a weight that is representative from its performances. Second, we would promote variety in frequency standards. So not only we discourage with option 2 to focus resources on the single species, but also option 2 really relies on the availability of frequency ratios. So we would encourage institutes to measure new and renew measurement of various frequency ratios. So third, this option 2 can be implemented right now because it only relies on the global fit of frequency ratio that was detailed thoroughly by Helen in the first talk. Another interesting property of option 2 is that it's able to mitigate the risks. So we discussed about errors in possible frequency ratio measurements. So first, we should notice that there is no possible error in the definition itself because the definition is some kind of an arbitrary choice we make and that is fixed. But there can be errors in the realizations of the second. And so for option 1, it's only problematic if there is a problem in the primary frequency standards. But if it happens, then there is a high impact on the realization of the second. On the other hand, for option 2, there is a higher probability that it happens because it can happen to any transition in the definition, but it has a mitigating impact because it's average over all possible transitions. Okay, and another specific advantage of option 2B, so this version with adaptative weights, that we are able to adapt to the evolution of frequency standards and possibly add new frequency standards as they become available. So disadvantages of option 2. So a key feature is that there is no more primary frequency standard. So there is not a single transition with zero uncertainty on recommended frequency. But as we have seen, actually this added uncertainty is hopefully smaller and maybe much smaller than the actual clock uncertainty. And in a context where there are multiple frequency standards, so for instance, the relation of 𝐸𝐸𝐼, actually option 2 gains with respect to option 1 because the uncertainty is average over all possible transitions. Another disadvantage of Thorium 2 is the fact that if we don't pick up a single transition, we might confuse industrial who would not be able to decide on a specific transition to develop new clocks. But as was pointed out by Ekkehard just before, actually, industrial need is driven by market. And so there are already quite a lot of developments of other species than cesium, rubidium, and optical clocks. So we think it's going to continue with a new definition, whatever it is. So two other disadvantages of option 2 is rather the presentation of the options. So it might be a bit difficult to explain, but so geometric mean is not a tool that is available to anybody. So, but on the other hand, I mean, it's possible to explain option 2 without math, just putting forward the concept of average, which is easy to understand. And last, the constant n loses physical interpretation. So for option 1, n is the number of oscillations of such species in 1 second. In option 2, it has no physical interpretation, just like this one. But on the other hand, you know, n is an arbitrary constant. It's just there by accident, just to match a previous definition. So it's not so important that it has a physical interpretation. And for option 2B, as was pointed out by Ekkehard, so the phrasing of the definition is quite different from what we are used to, but I mean, that's the price to pay. Okay, I will just skip this for the sake of time and jump to the conclusion. So in the end, option 2 is a definition that involves many transitions instead of one, with let's say an objective criteria for inclusion based on their performances. And the key feature is that it's possible to fairly balance the uncertainty on the realization for over all transitions so that they can all contribute to their best to the realization of the SI second. And last feature is that there is no more development needed. Everything that is required for option 2 is in place, the fit of frequency ratio, but also the steering of 𝐸𝐸𝐼 that is currently done with secondary representation of the SI second. And I conclude with a few references that were published about this option 2, and I'd like to answer your questions if you have some.
So thanks again to Jerome and Tetsuya. I think we only have time for maybe one question because we're a little bit over time. Does anybody have a question for the speakers?
I'll just ask a very quick question. So it certainly seems to be prominent in all of these things that frequency ratio between different clocks is the predominant thing that's important here. But when it comes to actually ensuring that the clock is working properly, a comparison between same species clocks seems to be the most important to me. Right, if my life depends on the clock, I want to see that the two clocks can be built that actually agree with each other. So where does that come in this particular definition?
Well, here in option 2 as well as in option 1, there is no input to plug this agreement between clock with the same species, because in the end what we use is the fit of frequency ratios, which involves only frequency ratios with different species. Okay, so this being said, and I think that was done before for the fit, is that there is an overall manual check of consistency of the fit, and if somehow clocks with the same species tend to disagree, then some additional margin on the uncertainty on recommended frequencies can be put by hand to account for that. Okay, but this is all related to the realization of the unit. I mean, for the definition itself, there is no influence of frequency ratios. The definition is just set independently of these ratios.
Okay, thank you, Jerome, for answering that question. I see that there are some hands up, but we are running out of time for this because we have one more speaker and then we're supposed to have an open discussion. Can people who have questions for Jerome and Tetsuya actually put the questions in the chat, and the speakers can answer those individually so we can move on to the next speaker. So our next speaker is Stefan Weyers, and he'll be speaking to us today about fulfillment for the redefinition of the SI second, criteria and challenges. Your screen looks good, Stefan.
Okay.
Oh.
So can you hear me?
Yes.
Yeah, okay, thank you. Yeah, good afternoon. I'll try to make it a bit short and at least where there is some redundant information. So I will concentrate to report on the status of the fulfillment of the criteria for the redefinition, and the presented evaluation is based on the work of subgroup 2 criteria of the task force for the redefinition. This subgroup criteria was established in 2023 as part of the reorganization of the task force. It currently consists of 10 members from 9 countries, chaired by 𝐊𝐞𝐲 𝐤𝐞𝐫𝐬, Tetsuya Ido, and myself. And the main task of this subgroup is to pursue the status of the fulfillment of the mandatory criteria. As we heard before, these criteria must be achieved before we can go and redefine the definition. There are also 6 ancillary conditions which do not need to be completely fulfilled, but there should be some reasonable progress. And for details about the criteria and the conditions, please look at the 2024 Metrologia publication shown here at the bottom. For tracking the criteria and conditions, all the criteria and conditions were divided in three further subgroups, each considering 4 or 5 criteria or conditions. And the first subgroup is optical frequency standard status. the second optical frequency standard operation, and the third time and frequency links and dissemination. And accordingly, there is a division of the group members. Tetsuya, Sébastien Bize from 𝐊𝐞𝐲 𝐤𝐤𝐞𝐫𝐬 from NICT, they form the team for the first group. Myself, Marina Gertsvolf from NSC, Helen Margolis from NPL, they form the team for the third group, and for the second group, sorry. And the third group is built by 𝐊𝐤𝐞𝐲 𝐒𝐤𝐞𝐫𝐬, Pascal Defrenier from ORB, Carsten Rieck from RISE, and Paul-Eric Poty also from 𝐊𝐿𝐴. In the following, I will concentrate on the currently more important criteria and only say a few words briefly about the conditions at the end of my presentation. We need to note that there are currently 4 criteria in particular where the fulfillment is insufficient. And more quantitatively, this can be observed in this graph where the achievement level is plotted for each of the 8 mandatory criteria. So this graph represents the status of November 2024 when we had the last CCTF. And it is quite obvious that there was little progress in fulfilling the criteria since 2022, because the only progress is indicated here by the red arrow concerning the criterion 2.1, availability of sustainable techniques for optical frequency standard comparisons. So there is a group of 4 criteria where the fulfillment is already quite good. As I mentioned, I will just briefly say a few details about these criteria later in my talk. But more important, there are currently 4 criteria where the fulfillment is lacking. It's really insufficient. And now we will go through the 4 criteria where the fulfillment is insufficient. So the first criterion 1.1 concerns the optical frequency standard accuracy budget. And what is requested in this criterion are at least 3 optical frequency standards with the same reference transition, but in different institutes, achieving systematic uncertainties at the level of 2 × 10⁻18 or below. This is the first part. And the second part is that there should be at least 3 optical frequency standards with different reference transitions in the same or different institutes at the same uncertainty level. And the current achievement is that we have only 2 optical frequency standards with the same reference transition in different institutes at the requested uncertainty level. These are aluminium ion clocks at NICT and at Huazhong University in China. For the second part, it looks somewhat better. We have already 4 clocks, lattice clock at GILA, strontium lattice clock, and ytterbium lattice clock at NICT, and the mentioned aluminium ion clocks at NICT and Huazhong University. All of them fulfill the requirement of an uncertainty at or below the 2 × 10⁻18 level for the 3 transitions, strontium, ytterbium, and aluminium. And we also have the octopole transition in ytterbium ions, 171 ytterbium ions, which is close. So here we already have 2 optical frequency standards, at least with published uncertainties below the 3 × 10⁻18 level at NPL and PTB. So for this criterion, the criticality is that there is only a limited optical frequency standard number with the same transition in different institutes fulfilling this uncertainty requirement. So what is clearly needed are additional optical frequency standard evaluations at this uncertainty level, in particular for optical frequency standard, where we have already 3 groups active and as the elements or the transitions are listed here. So the achievement level for this criterion is between 30 to 50%. And for criterion 1.2, validation of optical frequency standard accuracy budgets, it is requested that there should be at least 3 unit ratio measurements, which says using the same reference transition between different institutes in agreement at a level of 5 times 10 to the minus 18 or below. And that there should be 5 non-unit ratio measurements using different reference transitions, and each ratio should be measured at least twice by different institutes at the same uncertainty level. The achievement here is that we have 3 unit ratio measurements at the requested uncertainty level, but all of them are in the same institute, either at NICT, PTB, or RICN so far. And for the second part, we also have 3 non-unit ratio measurements of optical frequency standard with ratio uncertainties, but they are below the 10 to the minus 17 level and not yet below the 5 times 10 to the minus 18 level. Please don't forget, this is the status of November 2024, so there is some development ongoing. Regarding the criticalities, it's clear we don't have even one of the required 3 unit ratio measurements between OFS in different institutes at this level, and we don't have even one of the required 5 non-unit ratio measurements at the required uncertainty level. So here also clearly more high-level comparisons are essential, either using fiber links or transportable clocks. And again, it's particularly desirable for the elements, the transitions where already 3 groups are already active. And unfortunately, here the achievement level is still below 30%. In my view, a very important criterion is criterion 1.4, regular contributions of optical frequency standards to TAI. And here are requested 3 state-of-the-art calibrations of TAI each month from a set of at least 5 optical frequency standards for at least 1 year. And state-of-the-art means that the uncertainty, the calibration uncertainty, the overall calibration uncertainty should be at the 2 times 10 to the minus 16 level or below, where the additional uncertainty due to the secondary character of the definition here is not taken into account. And additionally, there should be a check that if we take a particular standard or a combination of standard for the primary definition, that there is no degradation of TAI. So this should be checked. And in November 2024, we had contributing standards for the calibration of TAI, 8 optical frequency standards from 70 institutes. They have performed in total 140 TAI calibrations. But the criticality is there have not been 3 optical frequency standard calibrations of TAI every month for 1 year at any uncertainty level. And there has also not been even 1 month with 3 optical frequency standard calibrations at this 2 times 10 to the minus 16 uncertainty level. And also, I believe Helen mentioned it already shortly, also the number of TAI calibrations have dropped off in 2024, 2025. So what is needed are more regular TAI calibrations, and additionally, there should be high uptimes of these calibrations, and the duration of this calibration should be at least 20 days. So the meaning of this will become more clear with the next slide, but it's also related to that we hope to have a decrease of the satellite transfer uncertainties, because this would mitigate the request for this 20-day period evaluations, and the availability of more reliable commercial systems would mitigate the requirement, would certainly improve the problem of the limited uptimes. So here's a achievement level is 30 to 50%, and I would like to emphasize a little bit that we have a quantitative and a qualitative lack of fulfillment here. So the quantitative point is that since October 2014, when we had the first TAI calibration, until April 2022, we have now 161 calibrations from 9 OFS. So this number is slowly increasing from 8 institutes. But during the last year, on average, we only had 0.5 optical frequency standard calibrations per month, while we had, just for comparison, 7.5, on average, 7.5 cesium fountain calibrations. And with respect to the quality of the data, we need to note that the overall optical frequency standard calibration uncertainty, U, is almost always larger than the best cesium fountain calibrations, even without considering this additional uncertainty for the secondary representation of the second. The reason is that the intrinsic uncertainties, of course, of optical frequency standards, the statistical uncertainty UA and the systematic uncertainty UB, is usually much better than any cesium fountain uncertainty, of course. But additionally, we need to take into account the intrinsic link uncertainty ULEP and the TAA link uncertainty UL-TAI. And the intrinsic lab uncertainty scales with the uptime. So if the uptime is small, we get an increase of the intrinsic ULEP uncertainty. And if the evaluation duration is much less than 30 days, we get an increased TAI link uncertainty. And to demonstrate this, I would like to show this graph, which shows the calibration uncertainty of a few state-of-the-art fountain frequency standards. These are the symbols in gray for the period August 2008 until April 2025. So all these gray symbols are fountain calibration uncertainties, which significantly were reduced during the years, which is a good sign. So we arrive now at almost 2 times 10 to the minus 16. And the colored symbols are all the 161 optical frequency standard calibration. And it is obvious that there is only a handful of optical frequency standard calibrations which was better, or which with a smaller overall uncertainty, calibration uncertainty, than the uncertainty of the best cesium fountains. So there's also really need for improvement, qualitative improvement of the optical frequency standard calibrations. And finally, the fourth criterion where there is still some lack, it's a criterion about the availability and sustainability of transportable clocks or tramit frequency links with uncertainty of less than 5 times 10 to the minus 18. At least between NMIs operating the optical frequency standards of criterion 1.1. And I think most of you know that uncertainties below this level have been demonstrated, for example, in Europe and Japan. So we had comparisons using fiber links in Europe in 2022 and 2023, involving up to 11 optical frequency standards. There are also existing transportable optical frequency standards in Germany, Japan, and China at this uncertainty level. And in 2023, for example, there was a campaign with transportable clocks in Europe. Transportable clocks from Japan and Germany went to the UK and Germany. So the criticality is here mainly the sustainability of these links. And the good news is there are some planned new campaigns, and there is some improvement at the horizon. So we can expect more improvements here. And at least the achievement level is already somewhat below 70%, but not so bad. Just a brief look at the criteria with high achievement level. So the first one is with regard to absolute frequency measurements of optical transition frequency. So we have at least 3 independent measurements with an uncertainty below 3 times 10 to the minus 16 for strontium and ytterbium lattice clock, and another measurement for the octopole-ytterbium transition. The knowledge of the local geopotential at the proper level, this is also quite nicely fulfilled. At least today we have at 7 institutes high accuracy relativistic redshift determinations at the level below 10 to the minus 17, even at the small 10 to the minus 18 level. Then it is required that the definition allowing future more accurate realizations, this should be the case. And we can currently say there is no identified fundamental effect limiting optical frequency standard accuracy at the 10 to the minus 18 level. There are already a few frequency standards were published with an uncertainty in the 10 to the minus 19 range. And finally, there is access to the realization of the new definition. Here it is required that there is a realization, a mise en pratique of the new definition that must be easily understandable with a clear uncertainty evaluation process. And I can say that corresponding documents have already been drafted in subgroup 1 of the task force. Then also, we learned there should be a primary, secondary representations of the SI second. They will continue to be accessible via metrology institutes or TAI. And of course, cesium frequency standards should ensure a secondary representation of the new definition. So the overall achievement level of these 4 criteria is at least approaching 100%. It's not very critical, I think. So in the end, it's this graph which nicely represents where we are and which also shows where our efforts must go, in which criteria. Maybe I repeat, this is the status of November 2024, and a more formal update in the evaluation of all these criteria will be performed in August, September, before the next CCTF in September 2025. And there are some paper have been published. They are not included here in the judgment, and there are also additionally some publications in the pipeline. So hopefully our result of our discussion will be a significant improvement of some of the criteria here. Thank you for your attention, and of course I'm open for your questions.
Thank you to Stefan for the wonderful talk. Does anybody have questions for him? If there are no questions for Stefan right now, we're going to move on to the last portion of this technical exchange, which is an open discussion between audience members as well as speakers. Sébastien Bize will be moderating this discussion.
Hello, thank you, Tara. Thanks to all the speakers. So yes, I think now the idea is to open this technical exchange to broader questions. So maybe I will redo a very brief introduction while you are preparing your questions. And then, of course, I've seen on the chat several specific questions, and I think we will also have time to address these questions. So maybe that will be the starting point for the discussion. So if I can share my screen, yes. So it's just a very basic reminder, which, by the way, will repeat information already given. So for all this discussion, it's very important that all involved institute have the proper information. And so I'm repeating first what Marina already said. that on the BIPM website, there is a dedicated place where you can find answers to frequently asked questions. You can find the roadmap that has been mentioned several times, the link to the publication, some presentation given on the same topic. And also, I don't know if it was mentioned, but on this page, it's also giving a email address for receiving question, then will be suitably dispatched to within the working groups to have answers. And also I remind for the formal member of the CCTF that there is plenty of information accessible on the CCTF website. That is to say, all the documents that have been shown at the previous CCTF meeting. So again, this is very important to point out where to get information and to feed the discussion. Second, I also using the slide that were shown at the previous CCTF session, but maybe not everybody have seen that. Marina also mentioned this. So regarding the formal process at the previous CGPM in 2022, the situation was presented and the formal recommendation was made, suggesting steps towards the redefinition of the second. And this recommendation requested the CCTF to make proposal at the next CGPM, so at the 2026 CGPM, towards preferred choice of species or of an ensemble of species, and to make suggestions also or further step, having in mind the redefinition in 2030. So that's one of the very important points that we are addressing now, is to properly answer to this request of the CGPM. And so for that, there have been a first session of CCTF and plenty of other activities mentioned by Marina. And now, very importantly, we are preparing for this second session of CCTF in September this year, 2025. And given all the steps, that's practically where we have to prepare a new proposed recommendation for the CGPM 2026, trying to, as much as possible, address this. And of course, if this is done and possible, that means that the redefinition would apply, would be done in 2030. And of course, the question is that if this is not possible for some reason, that means that there will be the need to postpone. And I would say, I think Stefan showed very well that it's the meeting some of the criteria is a hard task. Of course, they are very demanding, but it's suitable to be very demanding. So I would say, now to maybe introduce the rest of the discussion, it's very important to address the question in the view of this need to make a sensible recommendation for 2026. But of course, what is exactly the sensible recommendation? It's in some sense open, but it could be, yes, we know exactly what to choose, and this is the species. It doesn't feel like that. It can be, there are several possibilities, and this is how we comply with the criteria. And in principle, and I guess potentially it could be something that really highlight the fact that being ready for 2030 is a big challenge. So so I would say about the options, you can have both some fundamental aspect and question, but there is also the practical question to make your mind and for the committees advance toward a concrete recommendation to be done at the next CCTF as a preparation for the next CGPM in 2026. So I think it's important to have in mind to say, okay, what are we aiming for on the short term? Okay. So that's it. I hope this aspect is clear, but if not, I'll be happy to clarify, and then I think we can move on to the more the open discussion. But as part of the open discussion, I suggest that those who ask a question in the chat, they ask it again so that we can get the answer for everybody. And in doing so, don't forget to raise your hand and open your microphone. I think some of the questions were really, interesting for everybody, and so it's really useful to get the answer to that. So, Niels.
Yes, so I can repeat my question that I put already to the chat,
Sure.
and it was about option 2. Whether I understood it correctly, that if we pick option 2, then an NMI that does not operate all standards simultaneously will be limited in terms of achievable uncertainty in the realization of the unit of time. And what I heard from the audience was that this would be the case.
Okay. So, Jerome, do you want to answer this question?
Yes, so formally that's correct. I mean, if you have only one species, you must rely on external frequency ratio measurements to be able to link this specific realization to the second. Okay. However, the point is that this improved frequency standards would also contribute to frequency ratio measurements, and so in effect reduce the uncertainty on this link itself. Okay. I think there is a nice sentence by the author Niels Nimitz, that a key appeal to me, this definition would motivate to actually compare clocks, not just rely on accuracy budgets.
And as a consequence, I would also complete that, on the short term, there is the recommended value and uncertainty, and this is limiting. But on the mid and long term, this value, this recommended uncertainty improves, and there is no limit to improving if measurements are done.
Yeah, it was more like from a fundamental point of view. I always had the feeling that the realization of the unperturbed frequency is something that depends only on the effort of each individual NMI. But with the option 2, it would really mean that a single NMI has to operate all of them if it does not want to be dependent on other NMIs work.
Yeah, I think that's correct, and it's highlighted in the pros and cons. I think even the one you can find, the fully realizing in complete isolation. That is to say, all measurements are coming from the lab. It's a harder task because you need to measure the ratio at least once and so on.
Thanks.
Okay, more questions. I think that there were at least one other question in the chat worth answering for everybody. Let's see, which one is it? There are a lot of them now.
Sébastien?
Yes.
There was one, I think, unanswered questions from Charles Beinhelm.
Sure, let's go. Maybe that was the one, in fact, that I had in mind.
Sure.
Charles, are you still there?
Yes, I'm here.
Okay.
So I did actually get an answer from Jerome for this, but I'll repeat the question anyway. So the question was about under option 2, in particular under option 2B, What happens if frequency ratios are measured and put out as publications, but later on it turns out that the uncertainty was underestimated for some reason? And Jerome, I didn't, maybe I could let you answer again, but I didn't quite understand your answer. You were talking about the systematic budget and saying that that wouldn't itself go into the weighting calculation. But isn't that just part of the frequency comparison? And so ultimately it's the frequency comparison's uncertainty that goes into all those weights.
Yes, so what I wrote is that in the algorithm to compute the weights, so if, for instance, if you have a clock that has an underestimated systematic uncertainty, okay, it's not a published accuracy budget that makes the transition have more weight. What makes it have more weight is actual frequency ratio measurements, okay, and not only a single frequency ratio measurement, but a redundant frequency ratio measurement. Okay, so a very good clock with a very good uncertainty, but with a potential mistake, would not contribute if it's not verified by frequency ratio measurements. Okay.
But I guess what I'm saying is I'm assuming that the systematic uncertainty is the limiting factor. So your instability coming from statistics is smaller than it, and so you've got some potential offset that's accidentally missed from your calculation. Sorry, is that consistent with what you said?
Yeah, I mean, here the key is redundancy. I mean, if you for having a large weight, you need two different frequency ratio measurements. Okay, so if you have a systematic uncertainty that was underestimated, it might show up in a mismatch in the global fit of frequency ratio. Okay, another possibility is that there is a common mistake that would be repeated in two different frequency ratios, but in that case, I mean, it's not tied to option 2. I mean, if we decide that we have to change the definition, then we have to choose a new continuity constant, and if there is a mistake in systematic evaluation, then there will be a discontinuity in the unit. But this is valid for whatever option that you choose.
Mm-hmm. Yeah, that's a good point.
And I would add that, you know, the question of is there a mistake in the recommended value? It's something that is in principle already present, because we are using the secondary representation are used for TI, and we are even asking for more. And so, you know, this is something that is already present. And
I suppose there's two different types of mistake. There's a mistake that causes the timescale to be slightly off, and that can be corrected by steering it back again. But there's also a mistake that causes the definition that's been programmed into a clock that's been sold to need correcting. And I guess that's a worse kind of mistake to make.
Well, I mean, if there is a mistake in a clock during the calibration, yes, it can happen, but again, I'm not. If this is what you mean, I think this it's something that is always present, and the way to deal with it is intercomparison, repeated to build confidence in the practices that are you know, in effect in the labs.
Yeah, I think it's right that options 1 and 2 are equally susceptible.
Yeah, exactly. You know, okay, we have two Niels, so Niels Nemitz maybe first.
Okay. So just in response to that, I believe you have a procedure at the beginning of the ratio matrix calculation by the linear optimization where you sometimes set increased uncertainties when there is an inconsistency in the measurements, right? Is that where it would happen?
Exactly, I think, and then maybe I will let Helen answer more thoroughly. But you know, on the CIPM paper that was explained thoroughly by Helen, you know, the whole procedure is done, and indeed one of the point is to look for inconsistency, and because the fit is redundant, we even gain information on the consistency, and if consistency of either identical measurements of the same thing or inconsistency that appear through the fit are there. We try to manage it in a reasonable way, but and this is answering to the comment by Murray Barrett. I mean, we rely on peer-reviewed publication. It doesn't mean perfect, but we do not, in general, we do not give ourselves the goal to redo a peer-reviewed publication. But of course, if there are some inconsistency, we interact with the various groups. But if there is something strongly wrong, I guess the way to go is to have a comment to the peer-reviewed publication and always more measurement to understand the situation. But I would say at the level of the working group, where we try to have define normative values and normative uncertainties, we try to do our best. And Helen described very well how it's parallel to what the co-data is doing. It happened that there are inconsistent measurements for the co-data, and nevertheless, it's relevant to have normative value that will then that take into account potential inconsistencies, and of course, with the hope that inconsistency will be solved by new measurement and more discussions. I would say that's how I would describe the process. Okay, then there was Niels, the other Niels.
Yes, thanks. So related with what Jerome was just saying, my feeling was a bit that in option 2, reproducibility seems to be more important than let's say the uncertainty in realizing the unperturbed transition frequency, and maybe you could elaborate a bit on that. So let's assume I operate in a perturbed condition, but the frequency is very reproducibility, because I would expect to have consistent measurement results. Nevertheless, there might be some maybe more academic offset to the unperturbed transition frequency.
Yes,
Jerome.
Yes, so the first point is that this possible offset does not affect the definition itself. I mean, the definition is set by the weights, okay, and but then, of course, when you realize the definition, if your frequency standard has an offset, then you miss the actual definition, and you have a wrong realization. But this is true for any for any option. I mean, if you go for option 1, you choose, for instance, strontium, and if there is a repeatable offset in all the strontium clocks, then all the realization will be wrong by this offset. Now, if you go to option 2, so you have a set of transitions. So let's say ytterbium, strontium, ytterbium plus, whatever. And then if there is an offset in the strontium clock transition, then all realization will be wrong, but only 1/3 of this offset, because the other clocks might not be as wrong.
But in contrast to option 1, in option 2, you would gain weight. In, let's say, option 2B, you would gain weight if you can produce a very consistent output frequency.
I think you should recompare what is comparable. So option 2A is really, you set the definition once and you don't touch it anymore, so it's completely equivalent to option 1, where except that it has more transition. Okay, and now the question is what to do next if it turns out that the frequency standards improve very fast. We have more standards coming in with better uncertainty, and then you have two possibilities. Either you say, okay, it doesn't matter, the definition is good enough for application, we stay with the same definition, or you update the definition. Okay, and of course, each time you update the definition, there is a risk of discontinuity, regardless of option 1 and 2. And so the point is that option 2 via option 2B allows to do more updates frequently, because the update process is a bit smoother. You see, if you go for option 1, you have to change from one species to the other, so you radically change the definition at each update. But if you go for option 2, then it's possible to finally adjust the weights each time you have improvements. Okay, but the point is that if you choose to go for the way that you update frequently, then yes, each time you have an update, you have a risk of discontinuity. So you have to be sure that the frequency ratio are well understood. And but this is the case for option one. I mean, you cannot compare. Okay, I choose to redefine frequently with option 2 and never with option 1, which are two different situations.
Thanks.
Can I ask a question in relationship?
Okay,
oh, sorry.
Yes, maybe Christophe first and then Murray. I don't see your hand, Murray, sorry.
I have a short question to Jerome. Do you have a process in case of inconsistency in the ratios? Do you have a procedure to attribute the weights that you have discussed before, or or is it an ad hoc increase of uncertainties? How do you deal with inconsistency in the ratios?
Yeah, the point that least square don't deal well with inconsistencies. So the formal procedure has no predefined way to deal with that. So I guess the correct way would be to do what has been done with the global fit so far. I mean, to spot inconsistencies, and when there is an inconsistency, we just increase the input error bar of the ratios that are involved in this discrepancy, and then put that back in the input of the fit and get new uncertainty and new weights for recombinant frequency.
So it is a trial and error in the way you do that, essentially. So maybe it's a question to Helen. You have to increase the uncertainty somewhere, or you are able to identify the culprit, whether it's a link or a clock systematic shift. And then what do you do, actually? You increase the error bar until it's not visible, or?
So I think these are exactly the questions that we spend a lot of time discussing in the working group.
Sorry, it's a naive question.
No, it's not, and it's hard to give a single answer because I think it does depend on the specific case we're considering. So sometimes, yes, you can identify the likely culprit, but the reality is that often we don't have enough data to figure out where it is. So then you have to do something else, which is maybe expand the uncertainties on a subset of data because you don't know which one is wrong. And that's sort of what co-data do, actually. They increase uncertainties on subsets by some uniform amount, bring the chi-squared into some kind of reasonable range. But again, it only deals with statistical uncertainties, not unidentified systematics. So, yeah, it's difficult.
Thank you.
Okay, maybe there was one person before Murray actually already in the queue. Yes, Vernon, go ahead. Go ahead.
Okay, thank you. I'm just interested in option 2B regarding the multiple clocks, optical clocks. At different altitudes, I'm interested how you guys handle the systematic, especially the gravitational redshift. How do you deal with those different optical clocks at different altitudes? How do you handle or correct the systematic shift?
Mm-hmm. Okay, maybe I can start to answer and somebody else can say a bit more. So I think it's something that is not really specific to option 2 or option 1, because even in option 1, if you want to compare the clock or if you want to realize TAI, you have to deal with the gravitational potential. And so, and this is the reason why it's identified as an important criteria to enable a better redefinition of the second, including contribution of TAI and capability to do remote comparison. And then I would say the the one important thing to note about this gravitational potential is that the definition of the time scale, and it's in the 2018 CGPM Resolution 2. It specifies that it specifies a reference potential, and if you're not at this reference potential, you have to know the potential to connect to this reference potential. That's one point worth noting here, maybe to understand the logic. And finally, how do you know the potential? You have to rely on geodesy information coming from geodesy at your specific site. Potentially we can give you and to everybody a number of reference. There are a number of papers, I think most of them in Metrologia or Journal of Geophysics, where this task is described in detail. And so if somebody is interested to understand how to do that at your location, you'll find how it works. So, to give a really quick overview. I don't know if somebody want to complete my answer.
Thanks. I think I'll...
Go ahead, sorry.
Thanks. Tara?
Oh, I just wanted to mention that we're a bit over time, so we're almost at 15 minutes past the end of the technical exchange. I think it would be good to take a last question from Murray, because I think he's been trying to turn on and off his... I don't know if he's having access with turning on his hand.
Yeah. Okay. Go, Murray.
Could I ask one poll of the audience, because you guys have all heard these beautiful talks on people's perspectives on redefinition of the second. I'm curious if people have very strong opinions, or if you've heard something that's really convinced you. What does the audience? You could just put in the chat. What option would you prefer? Based on the conversations today, I'm just curious. And then I'm handing it back over to Sébastien and Murray.
Okay, Murray.
Actually, related to an earlier question about option 2 or whatever. So my original understanding of that was that one of the benefits, if you wanted to think of it like this, is that if it turned out that one clock was certainly much superior than others, then it would tend to have a weighting that would evolve, basically making that the default single option. But if I now understand what I heard here tonight, it sounds like it's more defined strictly on frequency ratios between different species clocks. And so that definition can't evolve like that, right?
Jerome?
Well, I'm not sure I understood the question, actually. Sorry.
So in terms of the evolution of those weights, in terms of, if certain clocks become obviously much better than the others, then they get more weighting. But the way I understood it tonight is that those weightings are always based on frequency ratios between all the different clocks. So one could not outshine all the others because it's always based on a ratio.
No, because you see, in the way the weights are attributed, we try to extract from the uncertainty on frequency ratios the most likely uncertainty of a single species. So, for instance, if you have 3 species, okay, and you have one species is much better, okay, so the uncertainty will be U for this the ratio between this good species and species 1, also U from between this species and species 2, and square root of 2 times U for the frequency ratio between the 2 other species. And from there, the algorithm to determine the weights would put a larger weight on the best transition, even if there is no other transition that is as good. Okay, the only way it can fail is that if this better transition is 100 times better than the other 2 transitions, for which the 3-corner hat method would not be an exact, an accurate estimate of the single clock uncertainty. But it doesn't matter so much because the weight would be already close to 1.
Okay, cool.
Okay, so as maybe okay, I see Patricia as
Yes, I don't have a question. I would just to say thanks and to remind that this meeting has been recorded and it will be published on the capacity building list of video related to the technical exchanges. And also, if you can give us your presentation, they will be stored in the CCTF web page. And if you agree, they will be open to the public, not only restricted to the participant of this meeting. Thank you.
Okay, so like Tara said, we are short on time. So I think one last even point that I would like to stress again, at this point, I think it would be very useful to ask yourself, is the information on all that we have discussed properly there, or for example, do you identify gaps that, according to you, prevent you from making your choice? This is the kind of information that would be very useful to have, or if you look at all the material, is it, do you feel that you have enough information to make your choice or start to make your choice? I think that is very important. And the second point, if you give feedback via the email address, for example, of the BIPM's website, also, I think it's important to have in mind this, short-term deadline that we need to prepare a recommendation for the next CGPM, and that the time for doing that is September 2025. So not everything this is complex, but nevertheless, keep in mind that we also want your feedback to, make this decision on the short term. But this decision can be, the different possibilities that I mentioned with respect to being ready, completely ready, or not ready at all, to make it short. So I think it's important to always have this in mind when thinking about that. So thanks, and maybe I will hand it over to Tara to conclude.
Just
finally.
A quick question. Will there be an update in September 2025 about the table that were shown today?
So, as Helen said, we are for sure producing an updated set of recommended values. That's one. And as part of the working group on options and everything and criteria, we are also updating everything. And I think all this will be taken into account and shown at the CCTF and part of the decision. So, for example, already the fact sheets we have updated. We make a last update just before the meeting and so on. So yes, we are taking into account. But, and by the way, thanks for asking the question. Regarding the formal process of recommended value, I remind everybody that the deadline for peer-reviewed publication to be published is June 30th. So forget about the questionnaire. If you have something not in the questionnaire, but published on time on June 30th this year, we take it into account. After, it will wait for the next round of updates. So, Tara.
Hi, Sébastien. Thank you so much for moderating that discussion. I'd like to thank all of the speakers who have contributed today, and also all of the participants who have come to listen to this technical exchange. I just want to share one last slide. Let's see if I can find it. Here we go. Can you guys see this?
Mm-hmm.
So upcoming with respect to the BIPM-CBKT program, we have two more technical exchanges that will be coming up. One on June 25th on timescale or algorithms, and another one July 9th on time transfer through GNSS pseudo-range measurements. Also, we have two UTC summer schools, one in May, which is almost just in 1 week, in Querétaro, at CNAM as part of the, jointly with the IFCS-EFTF 2025 meeting, and another in September 2025 at the BIPM. Also, you can you can keep up to date on some of the CBKT e-learning programs. So we have upcoming courses that will be released. And once again, if you have any comments, questions, or strong opinions regarding this, these presentations that were made today, feel free to email us at redefinition.second@bipm.org.